In this tutorial, you learn to monitor particulate matter, in other words, pollution from particles. You will transmit data via Wi-Fi and MQTT, and your setup will operate off-grid, making it suitable for designing citizen science or consumer products. In the description below the video, you will find a link to a GitHub repository that includes a wiring schematic, the bill of materials, and detailed explanations for each line of code. But first of all, let's have a look at a bit of theory. You'll measure particulate matter, which means microscopic solid or liquid particles suspended in air. The source of airborne particles could be combustion processes in industry or road traffic, but also cooking or pollen. As far as human health is concerned, you're looking at particles below 10 micrometers. However, the size of a particle says nothing about its biochemical reactivity and harmfulness. One thing is certain: the smaller the particles, the higher the chance they can reach the depth of your lungs or even enter your bloodstream. The mass concentration of airborne particles is typically measured in PM2.5 and 0.1 in micrograms per square meter. But research shows that for the most dangerous particles below 0.1 micrometers, the number concentration is the more relevant metric. In recent years, many low-cost optical particle counters appeared on the market, and some measure PM2.5 quite reliably, like the Sensirion SPS30 we're using here. OPCs detect particles in an airstream that passes between a laser and photodiode, and clever algorithms translate the signal into numerical output. Despite their shortcomings, OPCs are well suited for citizen science or consumer products. Here, measurements were taken every 5 minutes over 1 day, at a distance of 3 meters in an open kitchen and living room environment. When cooking, the values increase almost instantly and take a long time to go back to normal. To track indoor pollution events, a cycle time of 5 minutes is reasonable. On the other hand, if your cycle time is too long, you only capture attenuated values. In other words, you need to choose the cycle time wisely, depending on the type of particle pollution you want to detect and measure. Ideally, you want to monitor pollution and its magnitude for longer periods, like a month or a year. This is what we try to accomplish with the setup and code in this tutorial. In unattended long-term off-grid operation, there can always be Wi-Fi or power disruptions. Here, the setup automatically resumed its job after several hours of Wi-Fi failure. When you develop off-grid designs, you want to minimize energy consumption, running each task as quickly as possible. Because of the way OPCs work, they consume most of the energy per cycle, while the data transmission aspect is negligible. The calculated runtime and the actual runtime come fairly close, but never rely on calculations alone. Always test your setup and measure the current. Finally, you must consider battery capacity and battery depletion. Before you reach the battery's cutoff voltage, or better, before the supply voltage goes lower than the operating voltage, the battery should be exchanged. Ideally, you track the battery voltage and transmit its value alongside the data. Then you can trigger a depletion alert message via email or text. We'll look at that particular aspect in another tutorial. So, let's have a look at the code to see how it works. The program flow may look a bit different because there's no loop with repeated instructions. Everything happens in setup because all possible end states and in deep sleep enter reset after a specified time. First, we include the libraries to communicate via Wi-Fi, the MQTT broker, and the sensor. Then we declare some constant variables for the Wi-Fi credentials, for the router channel, for the MAC address that you can find with the other code from the GitHub repository, and a fixed IP address that you set in your router. You also need the server details and Adafruit IO credentials. For this project, the free membership tier is sufficient. Then you instantiate Wi-Fi, sensor and MQTT objects, as well as feed objects for the data you're transmitting. Finally, you declare constant and changing variables for your timing needs and sensor readings. Everything needs to run only once, ending in deep sleep with a reset, which is why we put all the code into setup. After your device wakes up, you switch off the radio to preserve battery capacity. You initialize the I2C bus, wake up the sensor, enable the measuring mode, and wait for 16 seconds until the sensor's fan and particle concentration in the measuring chamber have stabilized. Then you take one reading per second for 30 seconds, calculate the average, exit the measuring mode, and put the sensor to sleep to preserve battery capacity. Now that you have the data, it makes sense to wake up the radio and connect to the Wi-Fi router, which should take less than a second with the method we are using here. You try to connect for 2 seconds, and if no Wi-Fi connection can be made, you put the device back into deep sleep and try again later. Now you try to connect to the Adafruit IO server and MQTT broker for 1 second, and if that fails, you put the device back into deep sleep and try again later. Finally, you can publish the data, disconnect from Adafruit IO and Wi-Fi, and put the device into deep sleep. So, let's see the whole thing in action, although, apart from the data arriving every cycle, there isn't so very much to see. To speed things up a bit, we're using a 2-minute cycle based on 49 seconds data acquisition and 71 seconds deep sleep. On the left, we have our setup acquiring and sending data, and on the right, we see the data arriving in an Adafruit IO dashboard. In case of an acute pollution event, you can take spot measurements anytime by pressing the button. One and a half hours of operation are compressed to 2 minutes for this video. To keep it simple, I kept hardware to a minimum because the clever stuff happens as always in the code. Here's an overview of all parts in case you're not yet familiar with them. You'll need the specified components, but you can find cheaper substitutes online. The wiring of this setup is very straightforward. And now it's your turn. Thank you for watching and listening.